Welcome back. This is part two of my lecture on classification and regression trees. So just a quick recap of what we've done so far. I stated an algorithm as a function, but let me describe that algorithm to us in English. One of these CART, so classification regression trees, is fitted as follows. We're going to build this model up one node at a time so that we only introduce splits. We only fragment our data when we need to, in that the function is changing and we have enough data to support a split. So what we end up doing is we search every variable for some split, and we select the one that gives the largest reduction in RSS. So this is kind of like forward selection, where I'm searching variables to see which one is going to improve my fit the most. Now, once I find that split, I end up with a bin smoother. So this was the page that I had last time. I just average the y's in that bin, and that becomes my fitted value. I summarize the errors with the usual residual sums of squares that we've been using with regression. The only thing that's new here is, I hinted at the stopping criteria, but I haven't mentioned pruning. So the stopping criteria is whenever I find a split, I'm going to check some criteria to make sure the split is important enough to include. So there's a couple rules that we use. So if the reduction in RSS falls below some threshold, so if it doesn't help me by some minimal amount, or if some of my nodes are very small, so if two of the children are very small in the split, one child out of the split is very small, then I'm not going to introduce the split. But let me caution you on this. It turns out that a good strategy is to overgrow your tree. So this is one of the main improvements that CART offered over some of the earlier models at the time, like AID and CHAID were two methods that had been proposed before then. So CART overgrew the tree, and then what's going to happen is it's going to do a backward pass called pruning. So you prune a tree, you snip the branches. So the whole idea is you want to overgrow the tree because there might be, for example, interactions that don't show up with a single split. You need two splits in order to model that interaction. So the best strategy then is to overgrow the tree and then get rid of all the branches that it turns out you didn't need. Okay, so this pruning is like backward selection, where you try to get rid of splits that don't help you much. You introduced them, but it turned out you really didn't need them. All right, well, let's go look at another example. I walked us through the wave example before, which involved one predictor. And so just as a quick review, this was the wave example. And so we had p equal to 1x. What happens if you have p equal to 2 x variables? Well, let's go through an example in detail. So I have a data set which is called ArtMuse. And so this is how many times have you been in an art museum as a function of your education and your age. So let's go regress the number of times that you went to an art museum last year as a function of these two variables. Now, I'm going to do one thing that's new here. I'm going to specify an argument called mindev. So that's minimum deviance. So this is going to be allow a node if the change in deviance is greater than this number times the deviance of the null model. So that's the deviance of the root child. And so this is a way to tell the carp function to overgrow the tree. And then I'm going to go prune it back. There's a function in R called prune.tree, and it will select the tree with the number of terminal nodes that you specify. So this is going to give me an 8 terminal node tree. So let's go look at this tree. So a couple things. If I plot the tree, an option that I often use is type equals uniform. Otherwise, these labels often get bunched up. So I will do that. Then I can add the labels with text equals the fitted object. CEX equals 0.8. CEX stands for character expansion. And this just says reduce the font size to 80% of the original font size. And otherwise, the fonts are too big and you couldn't read the numbers. So that's another thing that's very useful. Last time I showed us a function called partition.tree. Partition.tree, in the case of a bin smoother, gives us the fitted function shown as basically a step function. When you have two predictors, it gives us a plot with the two x variables plotted against each other, and then it shows the bins on this plot with the height. So picture a height. This would be a very high step coming out 5.14, and then you would see this is a very low step, and so forth. So this partition.tree is a very useful function. What I thought we could do is to walk through in detail how this tree got built. So maybe I make this just a little bit smaller. I hope you can still see this. Maybe let's go make it bigger again. And I'm going to walk us through it on the right-hand side. So let's put age over here. And this is education. And you're going to see my education variable only takes 8 values. So 1, 2, 3, 4, 5, 6, 7, and 8. And age was, this was a survey, and so there were actually 12 values. So let's say this is 6, this is 12. We'll make this the value 3. We'll make this the value 9. So let's just talk through what the algorithm does. So we start out with the root node. We have about 2,600 observations. This is the starting deviance, so 593, and the starting mean is 0.53. So then we go through and we search every possible split. So I think I have 11 possible splits on age. I have 7 possible splits on education. And it's going to find the split that reduces my sums of squares by the most. So it turns out that split is on education, and it says we're going to make the left child all values of education less than 4.5. So that's up here. We see it on our dendrogram. And on this figure, this would be our first split. So I'm going to put over here node 2 and node 3. That'll be my notation that I use. So what happens next? Well, we would pass all of the observations sitting off in this part of the plot to our build tree function, and it would find the best possible split. So it would try splitting education here, here, and here, and then it would try all 11 possible age splits, and it would find a split at the value of age at 1.5. So let's see, this is 2, this is 1. So this down here is going to be node 4. I'll just put a little circle. We'll call that node 5. I better circle those up there as well. All right, so we can see we've now partitioned the left child. So think of, here's education less than 4.5, here's education less than 1.5. What do we do next? Well, we would go pass the left child through our build tree, and it would search every possible split. Now, in this case, there are only 3 possible splits, and we find out that it doesn't help us. Okay, so none of these splits really improve the fit at all. Therefore, the function would just exit without doing any split. And what we have then is a terminal node. And so that terminal node is clearly shown over here, and I'll just write in the predicted value. So we could say y bar, or y hat, it's the predicted value, which is the mean, is going to be 0.51 something or other. All right, what would we do next? Well, let's go search the right child. So that would be up here. And I would go try all these different splits of age. I would then try all these splits of education, and I wouldn't find anything. So we run into another terminal node. And so what you'll see is that there's about 37 cases that go to this left child. We have about 857 cases that go to the right child, and we declare this a terminal node. So y bar, or y hat, whatever you want to call it, is 0.18 up there. Now, I want to just point out one thing. When I did this second split, the second split ended at education equal to 4.5. So I did not carry this off to the right. And why was that? Well, I'm only considering cases over here where education is less than 4.5. All right, well, let's move on. What happens next to my algorithm? So I have all the cases sitting up here, so people with education greater than 4.5 and any age, and we're going to go search for the best possible split. So it would search these 3 split points on education. I've got 11 possible split points on age. And what does it find? Well, it says, I want to introduce another split on education. So it's very clear on the dendrogram, we're going to have this split on education equal to 6.5. So I'm going to go draw another split right here, and we will call this, looks like node 6 is to the left of that line. So between this line and this line is node 6. And then node 7 is going to be over here. Well, these are not terminal nodes yet, so I'm not going to write in the predicted value. Well, what do we do next? Well, what we do next is we're going to search all cases where education is greater than 4.5 and education is less than 6.5. So that's this region right in here. And we're going to go look for the best possible split. So I could split education, or I could split age at any one of those points. What does the tree function decide to do? Well, it says we're going to split age at 5.5. So I'm going to draw this line right here indicating that split. So down here we have node 12, and over here we have node 13. So there's node 12, there's node 13. You can see we have about 500 and some cases down here. We got about 638 cases in the top part of that. Well, what happens next? Well, let's go search the bottom part of this. And so what you'll see is we're going to introduce another split. The best possible split would be at 3.5. So this would be this new split. Down here we have node 24. Up here we have node 25. So that's what that split is. What do we do next? Well, let's go try to split node 24, the bottom. Turns out we really can't find a good split, and therefore we make this a terminal node. So you'll see R puts a star next to terminal nodes. The Y bar value here would be we'll just call that 0.40 if we round it to 2 decimal places. Well, what do we do next? The answer is go try to split up what we had in node 25 which would be this whole region. So it turns out if we split age at 4.5, so this is 3, this is 4.5, we get the best possible split. We'll call this node 50 and node 51. What happens next? Well, it tries to split node 50, can't do it. Therefore, I'm just going to write the y-hat value, which is, call it 0.24. It's going to go search the right child, can't find anything meaningful. Therefore, we're going to just write in the y value 0.34. Then what do? Well, we still haven't searched up here. So let's go search up here. So that would be node 13. Notice R can't find a good split for us. Therefore, this is going to be the predicted value. Y bar is 0.43. Well, what do we do next? We still haven't searched any of this region off to the right. So can I find a split over here? And the answer is yes. We're going to split it at 6.5. So that's going to be the best split in that region. That beats splitting education at 7.5. It beats splitting any of these other education splits. So we're going to call this node 14 versus node 15. What do we do next? Well, we go search the bottom, can't find anything. Therefore, we're going to put in a predicted value of 0.49. That's coming from right here. If you round that to 2 decimal places. What do we do next? Well, we go search the top, can't find anything. So the function exits, and we're at 0.61. We terminate because there's nothing else left to split. So what I'm hoping you can visualize is a series of steps where this step is fairly high. So if you're highly educated and older, you tend to go to art museums. If you're a bit younger, you also go to art museums if you have a lot of education, but not as much as the older people. What's kind of a very strange thing is that we have found an interaction down here where young people with, I guess they're not old enough to really have gone to graduate school yet, because this age equals 1, I think is, 18 to 20 years old. So they haven't even finished college yet, but young people in this sample tend to go to art museums quite a bit. So if you're older with lower education, you don't go to art museums, but if you're younger, you do. Notice there are no splits out here, and it's probably because there is no data. You can't have a PhD if you're only 18 years old. I mean, I guess you could, but they're pretty rare. All right, so that's another example of how we build a tree in R. So in my next video, we will talk about classification trees, because we've only talked about regression trees so far.